The question that we're going to do over here is n queen problem, and the question asks you to place n queens on a n by n board so that no two queens attack each other, and then we return all distinct board configurations. Now the standard approach to solve this question is backtracking, which means we are going to place one queen per row and then track which columns and diagonals are already occupied. Now the key insight is that how the diagonals are identified. So every cell on a positive diagonal shares the same row plus column value, and every cell on a negative diagonal shares the same row minus column value. And then this will let you check whether a square is safe in O of 1 using 3 sets instead of scanning the board. And over here are the 3 sets that I've declared. So coming back to this quick picture, now each diagonal has a name. For example, a single number that is identifying that particular diagonal uniquely. So when you place a queen at one of the diagonals, it checks if the diagonal is occupied or not. So over here you can see the positive diagonal 0, 2, 1, 1, 2, 0. They all contain the value 2, and together they form one complete diagonal. And over here it's the same, 1, 0, 2, 1, 3, 2. They all give the value 1. So going back to our question, I'll run you through the code. The algorithm is working row by row, and now each row can hold exactly one queen. So we need to decide the column for each row. And when you reach row equals to n, that means all queens are placed. And then we convert the column list into a board string format. That's what we have to return. And also we are doing backtracking. So after each recursive call, we are going to undo the placement step as well, so the other branches can be explored. So I will run you through the code step by step. Over here we are creating an empty results list, and over here we are doing a n by n grid, which is filled with dot characters, so a period. And a board is a list of lists, so it's mutable, so we can place and remove queens as we explore. Now these are the 3 sets that we are keeping a track of. A queen is attacking its column and board diagonals. We don't need to set a row, or the way we have curated this algorithm, it is going row by row anyway, so we can only place one queen per row as per the design. This is our backtracking step. So it takes in row. So what this means is that, for example, row 0 through row 1 already have queens safely placed. So now we can try a queen in the next row. So this recursion moves down the board 1 row at a time, and that's why I said that we don't need to keep a track of row. This is the base case, which is essential for any recursive function. Now over here we are saying if row equals to n, which means you have fallen off the bottom of the board, meaning all n rows got a queen without conflicts. So it's a complete solution. So we convert each row of characters into a string, which means if you have something like dot q, maybe another dot, it's converted to dot q dot. So that's what this is doing. Now over here we are gonna try each column. So for current row we consider every column, and the if is asking that is this square attacked by any queen already placed, and then these are the 3 lookups that we are doing. And now is place, then we recurse, and then we undo. So this is the heart of our algorithm, which means places we put the queen down, record its attacks in all 3 sets. Then we recurse it. So we try to solve the rest of the board, row plus 1 onward. If it succeeds anywhere down the line, the solution gets appended to the result inside the recursion. And then this is the undo. So whether the recursion found solutions or hit dead ends, we remove the queen, erase its attacks, and restore the board exactly as it was, so the loop can cleanly try the next column. And then over here, this is the last step where we kick off our algorithm, and then we are starting at row 0. And when the recursion fully unwinds, the result will hold every valid board, and that's what we are returning.